section 5.9, oxidation-reduction reactions. So in an oxidation-reduction reaction, we get electrons being transferred from one substance to another substance. That's a lot of syllables, and so we often just call these redox reactions, read for reduction and ox for oxidation. A lot of redox reactions involve something reacting with oxygen, and that's actually where the name oxidation came from originally. Here, iron is being oxidized. It's becoming incorporated with oxygen. Oxygen is reacting with it. Okay. So here's an example of a combustion redox reaction. Remember, combustion is something reacting with oxygen. Here we've got hydrogen gas reacting with oxygen, and that forms water. This is a very explosive exothermic reaction. That's an example of redox. We can also have redox without combustion. Here we have sodium metal reacting with chlorine gas to form sodium chloride. Sodium chloride is an ionic compound. We've got sodium ions and chloride ions. And it came from sodium atoms and chlorine molecules. In order to become ions, they had to exchange or transfer electrons. And so that's where the redox part of that reaction comes from. So metals reacting with nonmetals are going to be redox reactions. Here's a couple of examples. Sodium with oxygen and sodium with chlorine. That's the one we just saw pictures of. We've got the elements with no charges, and then the product is an ionic compound. And so Na2O has sodium ions and oxide ions. Sodium chloride has sodium ions and chloride ions. So there's a conversion of free elements into ions, and that happens by the exchange of electrons, or the transfer of electrons. If one atom loses electrons, then there has to be another atom right there to take them. If there's an atom that's getting electrons, they have to come from somewhere else. There's no store or food bank or animal shelter for stray electrons, right? They're one atom has them or the other atom has them, and they can transfer them back and forth, but they're just not out there, okay? So we always have oxidation and reduction happening together. Atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. And that's one of those things that can be hard to remember. So oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And this is something that, I teach this stuff every semester, but I don't use it all the time. And so when I look at something to see if it's oxidized or reduced, what's going through my head is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Because if you don't use it all the time, it's really hard to keep straight. Here, the sodium atom has lost an electron. That electron is going to a chlorine atom. But oxidation is loss of electrons. This chlorine molecule is getting electrons. It's gaining electrons. So reduction is gain of electrons. So we've got horses need oats for clear brown eyes, and now we've got oil rig. So transfer of electrons between metals and nonmetals, where you're actually forming ions, is fairly easy to detect. Just looking at it, we can figure it out. But we can also have oxidation and reduction where there's not a complete transfer of electrons, there's just a shift in electron density. So here we have a hydrogen molecule and a chlorine molecule. And I use the analogy of the shared electrons as being like a blanket shared between two people sleeping in the same bed, right? And so here, hydrogen and hydrogen, these atoms are exactly the same. They're equally strong. They're equally wanting the blanket. And so the blanket gets shared equally. The electrons are shared equally. Same thing here between two chlorine atoms. But when the reaction occurs and we form hydrogen chloride gas, now we have a hydrogen sharing electrons with the chlorine. Well, the chlorine is the blanket hog. The chlorine is going to hog the electrons, and so there's a shift in electron density towards the chlorine. It's not a chloride ion, but it's partially negative. And this hydrogen is not a hydrogen ion, but it's partially positive. So the electron density gets shift, and so again, oil rig, we can talk about reduction being an increase of electron density and oxidation being a decrease in electron density. So those redox reactions between nonmetals are harder to identify because we can't see that there's ions being formed. And so we made up something called oxidation states to help us recognize redox reaction. So this is important to just get out there. Oxidation states are not the same as ion charges. They're not the same thing. Oxidation states are something we made up to make predicting redox reactions easier. What gets kind of confusing is that a lot of times the oxidation state is the same number as the ion charge. So the numbers happen to be the same. I'm like, well, that's confusing. Well, it is, and yet it also makes it easier. Because if you look at an ion, it has a -1 charge, that's its oxidation state. And so that's, I think, where we sometimes start thinking that oxidation states and ion charges are exactly the same thing, because a lot of times they look the same. So just be aware that oxidation states are made up. They're not real charges. We just made them up. So there's a set of rules for assigning oxidation states, and as is often the case, writing out the rules makes them look a lot more complicated than they actually are. This page here is really saying if there's an ion charge, that's what the oxidation state is. If there's no ion charge, there's no oxidation state, it's 0. So if we look at elements, there we go. I don't know how many, I jumped so many. So elements, element copper, does it have a charge on it as an element? No. So no charge, the oxidation state is 0. Here's another element, chlorine, Cl2. There's no charge, right, on elements. So the oxidation state is 0. So anytime you have a free element, the oxidation state is 0. If you have a monatomic ion, just a single atom like calcium 2+ or Cl-, the oxidation state is the same number as the ion charge. So here calcium has a +2 oxidation state, chlorine has a -1 oxidation state. The oxidation states of the atoms in a neutral compound or in an ion have to add up to whatever the charge is on the ion, and this is the same way it works with ion charges. So when we have something like sodium chloride, this is -1 and that one's +1. They're ion charges, and they come together in such a way that their charges add up to 0. And that is the same for oxidation states. Here, H2O, that's not an ionic compound, but this is a neutral molecule. And so that tells me that the oxidation states of all the atoms involved have to add up to the overall charge on the molecule, which is 0. This is a polyatomic ion. So here, nitrogen and oxygen are going to have oxidation states, and those oxidation states will add up to the charge on the ion. Okay? So all of that is basically the oxidation state behaves like the ion charge. And so where we need some extra rules are for the nonmetals. Because we look at a compound like water or ethane or something, and there's no ions involved, and so how do we know what the oxidation states are of the elements involved? So this is the set of rules, and the way I think of this is FA 765. There's actually a restaurant, FA 76. I've never been, but I don't get out much, so I've heard it's good. So Fe765. Okay, we've got fluorine. Whoops, that's not what I meant to do. We've got fluorine. You're like, well, that's not an F. Well, it makes the F sound. There, it's an F, right? Fluorine, hydrogen, oxygen, 765. Fe765. Think you can remember that? Fe765. Okay, that's the hardest part of this. The oxidation state, this is basically the list of who gets to choose oxidation state first in this compound. And it goes in this order, Fe765. Well, what oxidation state do these elements choose? They choose the oxidation state that would match their ion charge if they were an ion. Okay, so again, oxidation states and ion charges like so close to each other. So if fluorine was an ion, it would have a -1 charge. If hydrogen is an ion, it's +1. Oxygen makes a -2 ion. The group 7As make -1, group 6A -2, group 5A -3. So CR, what's its oxidation state? 0. That's very exciting. How about CR3 plus? +3. So here it has a charge. Its oxidation state is the same as its charge. Well, we kind of already did that one. Let's make up a different one then. I didn't mean to do that. I don't want to do that. Brain's not functioning very well. Oh, this is kind of the same, but methane, CH4. Okay, so there's no ions in this. It's 2 nonmetals. So Fe765. There's no fluorine, but there's hydrogen. So the hydrogen gets to pick. The hydrogen wants to be what? +1. So hydrogen's +1, and there's 4 of them. So what does this one carbon have to be? -4, right? So here, carbon has a -4 oxidation state, and each of the hydrogens has a +1 oxidation state. SrBr2. Are there ions in that compound?
Yes.
Yes, it's an ionic compound. So we're just going to look at the ion charges. Those are the oxidation states. So what's the charge on strontium? 2+, right? So its oxidation state is +2. And what's the charge on the bromide ion? -1. So the oxidation state's -1. And you see there's 2 bromines. They're each -1. And so just like their oxidation states add up to 0, their charges add up to 0. They behave very similarly. SO3. Do you have any ions in there? No, because we just got nonmetals. Fe765. No fluorine, no hydrogen, we got oxygen. What does oxygen choose? -2, because that's the charge it would have if it was an ion. It's not an ion in this compound, but that's what it would like to do. And there's 3 of them. And then we have 1 sulfur. So what is the oxidation state for that sulfur? +6. Well, that's kind of big. It is what it is. Some things have a +7. NO3-. This is a polyatomic ion composed of 2 nonmetals. So we're still going to use Fe765, but unlike this one, it was a neutral molecule, the charges or the oxidation states add up to 0. Here, the oxidation states have to add up to the charge, which is -1. So Fu765, fluorine, nope, hydrogen, nope, oxygen. Oxygen, as we just talked about, is going to choose -2. And there's 3 of them. So we need to figure out nitrogen has to just be whatever is needed. So we could think of it this way. I have 3 -2s plus the oxidation state on that nitrogen, and that's going to add up to -1. So -6 plus x is equal to -1. X is what? +5. Any questions? This is one of those things that takes a little practice. So identifying redox reactions, we're going to look to see if things are being oxidized or reduced. And we can look at their oxidation states to see what's happening here. So this is another way of remembering what oxidation and reduction are, but here in terms of changes in oxidation state rather than loss or gain of electrons. So oxidation is an increase in the oxidation state. Reduction is a decrease in the oxidation state. Or we could say reduction is a reduction in the oxidation state. The oxidation state's going down, it's being reduced. Oxidation state going up, it's being oxidized. Increase in oxidation state corresponds with a loss of electrons. So oil rig is still true. So here we have carbon and sulfur reacting with each other. 2 nonmetals, there's no ions forming, so how do we tell if this is an oxidation-reduction reaction? We're going to look at the oxidation states of the reactants in the product. And both of these are elements, so they start at 0. Over here, CS2, Fu765, no fluorine, no hydrogen, no oxygen, no group 7, but there's group 6, right? And so sulfur gets to choose. Sulfur chooses -2. And then to make all the oxidation states add up to the overall charge, the carbon has to be +4. So now we can see the carbon went from an oxidation state of 0 to +4. It's going up. Carbon's being oxidized. Sulfur is going from 0 to -2. Its oxidation state is going down, decreasing. It's being reduced. That's the reduction. Any questions? So these are not forming ions, but if the oil rig thing makes more sense to you, you could say, well, oxidation is loss of electrons. Well, that would make it have a positive charge, right? It doesn't actually have a charge, but that electron density is shifted so that it is more positive than it was before. And reduction is gain of electrons, so this sulfur going from 0 to -2 is like gaining electrons. Use oxidation states to identify the element that's oxidized and the element that's reduced in the following redox reaction. So we're going to go through and we're going to assign oxidation states to each element. So here we have tin. What's the oxidation state? 0, just an element. Here we have nitric acid, HNO3, all nonmetals, Fu765. So no fluorine, but there's hydrogen. What does hydrogen choose to be? +1. And next in the list is oxygen, and oxygen chooses to be -2. And I'm going to write that 3 times because there's 3 of them, and it just helps us to see what's going on a little bit better. So then nitrogen is the last pick, and so it has to be whatever it needs to be. So I've got -6 over here plus 1, so that's a total of -5. So the nitrogen has to be +5. You see how that works? This is like, super simple arithmetic, right? But then sometimes it gets confusing anyway, right? So, if you need to write it all out, make an equation and solve it, don't feel bad about that. We just need to figure out what it is, right? Okay, so over here, SnO2. Well, is this an ionic compound? Yeah, because tin is a metal and this is a nonmetal. Okay, so then we just need to look at the ion charges. Well, what's the charge on the oxide ion? -2, and there's 2 of those. What's the charge on the tin ion? Well, we don't get it from the periodic table because that's one of those squirrely ones that can be multiple things, right? We're going to get it from looking at the oxygens. There's 2 oxygens, they're each -2, the neutral compound, and so the tin there must be +4. So we learned how to find the charge on these transition metals back in chapter, I think that was 3. And what we're doing here with the oxidation states is very similar for that last element that just has to be whatever. Okay, NO2. No ions here, Fe765. So again, the oxygen is going to choose to be -2. There's 2 of them, so what's the nitrogen? +4. And then we've got water, again, Fe765. Hydrogen is +1. There's 2 of those. And so the oxygen has to be -2. It has to be that, but it's also happy about it. Yes?
So you don't have to worry about the number in front of the equation?
No.
The balancing number?
No. So the oxidation states, we're looking at the chemical formula of the compound, not how many moles of it react with how many moles of anything else. Yeah, good question. So I'm going to erase these extra ones, because that was just to help us look at it. So now, to identify things that are being oxidized and reduced, we're going to look for things who have changing oxidation states. Well, let's start with the first one. So here's tin, it was 0, and what is it over here? +4. So it went from 0, to +4. Was that going up or down? That's going up. So that's being oxidized. The other way to think of it is, well, is the tin gaining or losing electrons? Is losing electrons if it's becoming more positive. Oil rig oxidation is loss of electrons. So let's look at hydrogen. Here hydrogen's +1. Over there hydrogen's +1. It's not being oxidized or reduced. Here's nitrogen. Nitrogen's +5. And over here it's +4. So nitrogen is going from, that's not what I wanted, from +5 to +4. Is that going up or down? Down. So the nitrogen is being reduced. What about the oxygen? Is -2 here? Oh, I forgot to erase that one. -2, -2, -2 is staying the same everywhere. There has to be, in a redox reaction, there has to be at least one being oxidized and one being reduced. You could have one being oxidized and 2 different things being reduced, but you have to have at least one of each, oxidation and reduction. Somebody gaining electrons and somebody losing electrons. So oxidation and reduction have to occur simultaneously. When an atom loses electrons, another atom has to take them. It's a little bit like, buying and selling stuff, right? So if I'm going to sell something to you, you give me the money. It's not that you just drop the money on the floor, right? Or that, I give you the thing and I just pull money out of the air, right? It has to come from somewhere. It's the same thing with the electrons. Okay. Then, like, all of that wasn't confusing enough. We have reducing agents and oxidizing agents. So let's think about movies and movie stars. So a movie star is the person who stars in the movie, right? They get their name and lights and get a lot of money. How did the movie star get that position? They were hired, but who helped them get hired? An agent, right? The movie star agent, their job is to get roles for the movie stars, right? So, but the agent doesn't star in the movie, right? So the reducing agent, its job is to get something else reduced. The oxidizing agent, its job is to get something else oxidized. I know this is confusing. I didn't make it up, believe me. So the reducing agent is the thing that gets oxidized, and the oxidizing agent is the thing that gets reduced. I know, right? That exact expression right there. What the heck? Okay, so here we've got 4 chemical reactions. We're supposed to identify whether each is a redox reaction or not. And if it is a redox reaction, identify the agents, the oxidizing agent and the reducing agent. Okay, so let's look at this first one. There's a couple different ways that we can recognize redox reactions. If you have a metal reacting with a nonmetal, it's going to be a redox reaction. But maybe you don't remember that, okay, because you've got lots of other things to remember. Well, look at what's happening here. Does this have a charge? No. So we could identify oxidation states, right? This would be 0. And over here, does lithium have a charge?
Yes, it does.
Yeah, it does. This is an ionic compound, right? So here's lithium with a +1 charge and chlorine with a -1 charge. And so those charges correspond to the oxidation states. So here we have 2 elements. They're both 0. And the lithium is going to a +1 ion, and the chlorine is going to a -1 ion. Their oxidation states are +1 and -1. Oxidation states are changing. Is this a redox reaction?
Yes.
Yes. Yes, it is. Okay, so then we have to identify the agents. Well, let's just look at who's being oxidized and reduced first. Lithium is going from 0 to +1. Is that oxidation or reduction? That's oxidation. So lithium is being oxidized. And the chlorine is being reduced. So if lithium is being oxidized, it's causing the other thing to be reduced, and so this is the reducing agent. They are exactly backwards. That's the reducing agent. The thing that's being reduced is the oxidizing agent.
Who came up with this?
I know, right?
Yeah. We got to talk to them.
And you could say, well, what is the purpose of this at all? Well, when we have a compound here that contains something that's being oxidized or reduced, we would say the compound is the oxidizing or reducing agent, not the element in the compound. So there's this very subtle difference, which for us, it really doesn't matter at all.
Yeah, it'll go over my head.
Yeah, so we're not going to worry about it. Okay, let's look at this one. This is a net ionic equation. Do we have things changing charges? Yeah, we do. This is going from 0 to +3, and this is going from +2 to 0. We didn't even have to really think about it too much. Well, which of these is being oxidized? Aluminum or tin? Aluminum, because its oxidation state is going up. So aluminum is being oxidized. I'm just going to call that ox. And what's it being reduced? The tin. But not tin metal, tin ion. Because there's tin metal over here. This is what we have after it's been reduced. So when we're talking about what's being oxidized or reduced or what the agents are, we're looking at the reactants only. We're looking at how they changed when they got to the products, but we have to pick one of the reactants, not one of the products. So if aluminum is being oxidized, what kind of an agent is it? It's a red agent, reducing agent. And tin being reduced is an oxidizing agent. Okay? So let's just, make sure that we can do the oxidation, oxidized and reduced. And then if you get a question where you have to do the agent, just switch them. Okay? So that one was also a redox reaction. How about this one? Is that a redox reaction? Ugh. Do we have to do all of those? Well, let's check the metals. Well, here we have two ionic compounds reacting. So this was a metal element and a non-metal element. And here we have two ionic compounds. And actually what this is a precipitation reaction. And no ions are changing their charges. They're just swapping partners at the beaker party. Right? So if we look at the lead here, lead with two nitrates, the lead here has a positive 2 charge. And over here, what's the charge on the lead ion? It's still positive 2. Lithium is +1 here, and it's +1 over there. So in this reaction, they swapped ion partners, but they didn't transfer any electrons. So this is not a redox reaction. And then this one, carbon and oxygen making CO2. Well, we could say, well, that's a combustion reaction, that's a redox reaction, right? We can also look at, well, we've got two nonmetals reacting with each other. This is probably going to be a redox reaction. Let's check their oxidation states. So again, we're starting with elements, so they're both 0. And here in carbon dioxide, how do we identify the oxidation states? Noodles. Fuzz 765. There's no fluorine, there's no hydrogen, oxygen. Oxygen gets to be -2. So what's carbon? +4. So carbon went from 0 to 4. Is that oxidation or reduction? That's oxidation. And the oxygen went from 0 to -2, which is reduction. So who's the oxidizing agent? The oxygen. And carbon is the reducing agent. Oxygen is the oxidizing agent. The oxidizing was named for oxygen. Yes?
Will it always be opposite like that, or one will be oxygen and then non-F, I think, okay, it's gonna be.
Yeah. The agents will always be opposite. So you look at the thing that's being oxidized, that's the reducing agent. The thing that's being reduced is the oxidation agent, because it's causing the other thing to be oxidized.
Can you explain number 3 one more time again? What do we do?
So number 3, we're told to determine if these are redox reactions. In order for it to be a redox reaction, the oxidation states have to change. There has to be a transfer of electrons, or the ion charges have to change. And so when we look at this lead ion here has a +2 charge. We can figure that out by looking at the charge on the nitrate ion. And over here, we have the lead ion with 2 chloride ions, and the charge on the lead is the same. The charge on the chloride is also the same, right? All the charges are the same. And this guy as a unit has a -1 charge. And over here, as a unit, this has a -1 charge. So even though we're not looking at the nitrogen and the oxygen separately, when you apply the rules, it's going to be the same. Yeah,
So it doesn't have to charge to form an ion
correct.
to have an oxidation state
Yeah.
reaction?
Yeah, so we don't actually have to form an ion, and that's what happens here. Carbon dioxide's a molecular compound. The carbon and the oxygen are sharing their electrons, they're not transferring them one to the other making ions. But they're not sharing them equally. So the oxygen has a little more of the electron density, and the carbon has a little bit less. And the oxidation state rules help us to identify that.
So, the agents, are they just referring to the atoms, or they refer to compounds too?
The agents would refer to the compound,
Okay.
but we're not going to get all picky about that. I don't think that's something that you'll need to remember.
Is it possible to have one where there's two different elements that are part of the compound that are?
You can have a compound where one element gets oxidized and another gets reduced. Yeah, there's all kinds of weird things that can happen. We're going to try to keep it simple.
Okay.
So in figuring out whether it's a redox, should the two questions we should ask ourselves are, did the elements swap electrons and did the charges change?
Mm-hmm.
That's how we'll figure it out.
Yeah. So if ions are formed where there weren't any, or if the charge on those ions changes, it's going to be a redox reaction. And then if you've just got the nonmetals, then you're looking at oxidation states. Yeah.
If formed a molecular, if it formed a molecule, and those molecules aren't a part of 5, 6, 7, would it have an oxidation state, or?
Okay, so that's a good question. I think the 765, I know it will cover all the bases in Chem 1A. Because pretty much any molecular compound, fluorine, oxygen, hydrogen, group 7, group 6, group 5, I mean, there's not many nonmetals left, right? There's like carbon. And the noble gases, they don't make compounds, so we don't need to worry about them. Yeah. This is one of those places where we are showing you a simplified version of things, but it's enough for what you need to be able to do. So we don't want to think about the more complicated things. Any other questions? Those were good questions. The activity series. So if we put a strip of magnesium into a solution of copper ions, those copper ions will turn into copper atoms and deposit themselves on the magnesium strip, and the magnesium strip will gradually dissolve. This is like what we saw with our copper solution when we put zinc into it, right? The zinc disappeared, it became ions. The copper, the blue ions in the solution, went away and became solid copper on the bottom. If you do it the other way around, though, nothing's going to happen. If you put a strip of copper in a magnesium ion solution, nothing's going to happen. So the reason this happens is that magnesium has a greater tendency to lose electrons than copper does. And so this reaction is spontaneous. The magnesium will lose electrons, the copper will gain electrons. Copper strip in a magnesium solution, nothing happens, because the magnesium loses electrons easier than the copper does. And so copper's not going to lose electrons to the magnesium, and nothing's going to happen. So we have a list of metals that allows us to predict whether a reaction will be spontaneous or not. And you do not need to memorize this list. It will be given to you when you need it. So the activity series lists the metals in order of decreasing tendency to lose electrons. So we show oxidation half reactions where metal is losing electrons to become an ion. If you turn that half reaction backwards, it becomes a reduction half reaction, and the two of those put together makes a complete reaction. So here's the list, at least a partial list. So lithium is the most reactive, it's the most easily oxidized, it has the strongest tendency to lose electrons. So this guy will lose electrons and react with any of these ions below it. Silver has the least tendency to lose electrons. It's just really not going to react with much of anything. I said silver, I meant gold. Silver is also pretty unreactive. Okay, so this is the list. And I've tied this list into this idea of the beaker party and people going to this party. So I said the metals are like males, and so this is a list of guys in a high school. The girls have made this list of who's the coolest. I used to say who is muy mas macho, but then that just became way too old and nobody knew what I was talking about. So lithium's the coolest guy, right? And gold is just nobody wants to go out with gold. Okay. Yeah, let's see if I can work that analogy in here. So what we have for a reaction would be maybe something, like lithium. So if lithium is participating, and we've got lithium reacting to lose an electron, and then, I don't know, let's not do nickel because that's a 2. Let's do silver. And so then this one, we're going to flip backwards. So this is going to show the reduction. And when we add those two together, the electron went from the lithium to the silver, and so it doesn't show up in the overall chemical reaction. So lithium metal plus silver ions, that will do a redox reaction, and it'll make lithium ions and silver metal. That is a net ionic equation. So let's make this silver nitrate, and then we've got lithium nitrate. Oh, that doesn't need parentheses. That's in the way. Okay, so this time, instead of both of these guys coming with a date to the party, lithium's coming by himself. What do you call that when somebody goes on their own and doesn't have a date when most people do? We used to call that going stag.
We don't use that. We don't know what that is.
You don't know what that is. Anyway, this guy's going on his own. He didn't bring a girl. Okay, Silver brought a date. Silver brought nitrate. They go to this party. They mix and mingle, and lithium and nitrate really hit it off, and they exchange electrons, right? And so lithium is going to leave the party with nitrate, and silver is going to go home by himself, right? Right? I know. Life is brutal.
Brutal. Even in the
So if the reverse happened and silver came by himself and lithium brought the date, would silver go home with the girl? No, because silver's still at the bottom of the list, and the girl's like, "No, lithium, he's the top guy. I'm going home with him," right? Just don't take all of this too far. So in here we see where the girl is, the anion. Here we're not seeing where the girl is, but why does silver have a charge? He's all charged up because he's got the girl. Okay? And over here now, silver is not have a charge, but lithium has the charge because he's got the girl. Okay? That's the best I got. I like it. Anyway, which metal is most easily oxidized? So oxidation is loss of electrons, right? So it has to lose electrons, and so we're going to go back to the list, the activity series. We're looking for sodium, chromium, and gold. So here's sodium, chromium, and gold. And this is showing us, this is losing an electron, this is oxidation. So the person at the top of the list is the most easily oxidized. Determine whether each redox reaction is spontaneous. So this is how I look at this. So zinc is going to the party by himself, and nickel has a charge. Nickel brought a date. We don't know who she is, but what this is saying is that at the end of the party, zinc is going to go home with the girl, and nickel's going home by himself. So this is implying that zinc is cooler than nickel, right? Zinc is hotter, you know, how does hot and cool kind of mean the same thing? I don't know. Zinc is more desirable than nickel. And so what we have to do is we have to go look at the list that the girls made and see, is that true? Is zinc higher on the list than nickel? Well, where are they? There's nickel, and here's zinc. So zinc is higher on the list. Zinc can steal the girl from nickel. So this one is spontaneous. Yeah, writing with a highlighter, not so much. Spontaneous. That will happen.
And it's spontaneous because it happens naturally, is what we're saying?
Yeah. Yeah, in Chem 1B, we'll talk about how you can make the opposite reaction happen, but you have to pay people off.
Oh, gosh.
I know, right? Yeah. It's not going to happen on its own. Somebody has to invest. Yeah. You got to pay her to go home with him. I don't know. Okay, so let's look at this one. Zinc and calcium. So calcium has the charge here. Calcium's coming with the date. And this is saying at the end of the night, zinc's going to go home with the girl and calcium's going to be left out in the cold. So this is saying, again, that zinc is more popular, more desirable than calcium. So we have to go look at the list. There's calcium and there's zinc. Now, calcium is more desirable. So what happens there is calcium came with the girl, and calcium is leaving with the girl.
Okay.
This reaction is not going to happen. It doesn't happen. And so we would say that is not spontaneous. It doesn't happen on its own. Okay?
Mm-hmm. And when you do this, you're looking at your reactants, the ones in the front.
Yeah. Yep. And again, we're going to keep it to the more simple examples. Yep.
Well, we have to memorize that list for the test.
No, you don't need to memorize the list.
Before we go to the next chapter, can we talk about what we need to memorize for this chapter? Because there's like 2 things, right?
Yeah, we can talk about that. So this is not an exhaustive list. There are other metals that aren't in this list. And so what usually happens on an exam is that I'll give you like a list of several different metals, including the 2 that you need, so that you can see who's more popular than the other one. Okay, but I may not give you the whole list, but I'll give you enough of the list that you can tell. I don't have that memorized myself. It's not something that's important to me. Yeah.
I'm so sorry. Could you
No.
go over again why the first one is spontaneous?
Yeah. over again why this one is spontaneous. So the way I see this in my analogy, zinc here is neutral, he's coming alone. Nickel has a charge because he's with an ion, right? He's got a date, he's all excited, right? And so then we go to the party and mixing and mingling happens, and this reaction is predicting that zinc is going to end up all charged up and excited because he gets to go home with the girl, and now nickel's going to be all flat and neutral. In order for that to happen, zinc must be more desirable to the girl than nickel. Otherwise, she wouldn't swap, right? She'd just stay with nickel if he's more exciting. So then we go and look at the list. We're looking to see, is zinc higher on the list than nickel? And when we go to the list, we see that here's zinc and there's nickel. And so zinc is higher on the list, and so he will steal the girl from nickel. It is spontaneous. Does that help?
Yes.
Yeah.